Hi guys, please have a seat. So thank you for coming. So we have Jakob and Stanley from Heineken, and they'll be talking about fusing machine learning with mixed integer linear programming. So let's hear from them. Guys, go ahead, please. Thank you.
Thanks for the nice introduction. So my name is Stanley. I'm working as a data scientist or operations researcher at Heineken, mainly in the commerce domain, focusing on optimization projects. And
I'm Kuba, Jakub Tomaszewski. I'm working also at Heineken as a senior data scientist, where I'm mostly focused on marketing mix models.
So yeah, welcome to our talk regarding the fusion of machine learning and mixed integer linear programming, or more generally, combinatorial optimization. Yeah, I'll mix it up with operations research as well, so I'll use those terms interchangeably. Yeah, so our mission at Heineken is to empower the organization to make smarter, more data-informed decisions through the use of yeah, machine learning and mixed integer linear programming, or operations research. And throughout the years, we've seen that the combination of the two can bring a lot of value to the organization, and that is like a superpower, I would almost say. But we've also seen a number of things that can go wrong, and some of the lessons learned we'll be sharing with you today. Yeah, so yeah, I'm going to assume that there's a lot of data scientists and machine learning engineers right here in the room, and you have your cool LLMs, your ChatGPT, all that fancy stuff, and I think there's a lot of talks today on generative AI, and I have to admit it works super well and it's awesome. But there's actually something that I find quite striking, and that is the fact that if you look at what an organization is all about, it's making hundreds or thousands of decisions every single day and over a sustained period of time that will actually determine the success of an organization. But if you then look at what like the LLMs and like ChatGPT, etc., are not particularly good at, then it's making those optimal decisions. And this is, on the other hand, exactly where combinatorial optimization and operations research shine at. So yeah, I find it quite striking. But yeah, that's the state where we are right now. And yeah, actually, when we start combining operations research and machine learning, there's quite a number of things that can go wrong, as I elaborated on earlier. So we'll be diving straight in. So I want to start off with a few everyday examples of services that most of you are probably using on a frequent basis. So starting off with kind of a no-brainer, electricity. So electricity is all around us. We charge our electric vehicles. Our laptops, like anything we use nowadays, is powered by electricity. And there's actually a lot of optimization going on behind the scenes that I guess a lot of you are not aware of. And I'll be discussing a bit more on that in a second. Then secondly, when you open up Google Maps or Apple Maps, you'll actually that's not something that you see, but on the back there's actually a lot of optimization powering these applications to get you in the most optimal way from A to B. And then for the online shopping fanatics out there, when you place an order online and that package that's scheduled to arrive at your doorstep, there's actually a lot of optimization that is going into the supply chain, into the warehousing, into the routing to get that package at your doorstep. And yeah, if we let go of that optimality requirements that those systems usually have, then yeah, I can tell you that this delivery man there on the screen would look a lot less happy. So if we take that a bit further, if we let go of those optimality requirements, we will actually see that a lot of things in our society will start to break. For example, power outages would be occurring very frequently, and it would disrupt society. Traffic jams would become the new normal. And like, for example, there was a few years ago a 12-day traffic jam that is said to could have been prevented to a large extent if they would have done more optimal planning and routing, and that could have made quite a difference. And then lastly, that package that was scheduled to arrive tonight at your doorstep at 8 p.m. would hardly ever arrive on time again, and maybe wouldn't arrive at all and be stuck in that warehouse forever. So then zooming into the electricity grid a bit further, so on the screen behind me you can see the electricity grid of the US market. This represents around $400 billion annually, so it's a massive, massive complex puzzle where there's like many different sources of energy generation. There's hundreds of thousands of transmission lines with each having their own capacity. We have to balance the supply and demand in near real time, so it's like a super complex challenge, but yeah, through the use of algorithms such as mixed integer linear programming, we're able to tackle this challenge in near real time. If we now try to imagine how could we tackle such a problem through machine learning, then I think it would be super, super difficult. Like, first of all, if we take the example of XGBoost, for example, and we would try to tackle this problem, and then incorporating those millions of constraints, I would argue that it would be very, very difficult. And then let's say that we were somehow able to incorporate all those constraints in our machine learning model. Then there's yet another challenge, and that is the fact that the problem structure changes on a continuous basis, actually. And this would be very difficult for a machine learning, I would say. So yeah, one of the advantages of operations research algorithms in general is that it doesn't require any training or retraining. So this is a problem that we're not suffering of with operations research. Let me see. Then there's actually another issue. Let me think for a second. What was the other issue again? Like if we, again, relax that assumption that I mentioned earlier, then even if we could, incorporate all those constraints, then still the fact that machine learning doesn't have those optimality guarantees, it would mean that we're leaving millions or billions of dollars on the table, and that's something that we, of course, don't want. But yeah, as bright as a picture I may have painted about operations research and combinatorial optimization, actually we wouldn't be able to accomplish much without machine learning. And I would argue that the inverse is also true. So let me explain. So on the left for you over here, we have the field of operations research with all the different subdomains. Just to highlight one of the most commonly used, mixed integer linear programming. This is a modeling way where we have an objective that we try to maximize or minimize subject to some constraints, and then the decision variables are typically bound to be integer, or some of the decision variables are bound to be integer. And then on the right we have machine learning, machine learning models from reinforcement learning to deep learning, for example. And I don't have to bother you much with that, but those two fields, they may look quite independent from each other, but this is actually not the case, and they're actually very dependent on each other. So let's zoom into a few of the interaction effects that we typically see. So the first one, when you are trying to train your machine learning model, then you're typically trying to minimize some loss function. And this is actually like a non-linear optimization problem that you're trying to solve, where your objective is minimizing the loss, and you're typically going to let me think. So you're trying to minimize the loss, and the model parameters are actually the decision variables that you have. So like we try to minimize the loss, and then by doing that we actually are using operations research here in the machine learning model. So this is something super powerful that operations research is giving to machine learning. Then, secondly, probably the most common paradigm is the predict, then optimize paradigm, where we have a machine learning model that's trying to predict something that's going to happen in the future, and then we use those predictions actually to optimize some decision problem. This is something that we typically also do at Heineken, and that is something that we see being done in a lot of organizations. So this interaction effect is working out super well, because usually you have some decision that you want to make, and that usually involves the future. So then you want to use machine learning to predict that, and then you can use a operations research domain to try to optimize over those predictions. Then thirdly, dynamic programming is actually fundamental to many reinforcement learning algorithms. So we have usually an agent in some environment, and then we try to optimize the policy of that agent through actions and rewards. And what we then are generally using is the Bellman equation, where we divide the problem into subproblems. And these subproblems are usually then expressed in terms of the value of a state, expressed in terms of the values of other states. And through this recursive relationship, we can then estimate the long-term effect of our actions. So here again, we see that dynamic programming, although reinforcement learning is a bit more sophisticated than dynamic programming by itself, but dynamic programming is actually very fundamental to reinforcement learning. Then lastly, this is more of a research-oriented field, I would say, but for now. But there's usually, when we're solving an optimization problem, there's usually a lot of, every day we're solving the same problem, for example, and there's usually a lot of similarities in those problems that we're solving. So every day we might be looking at the same problem with slight variations in the data, but this is, of course, where machine learning excels at, and where we can really learn the patterns in the data, and then we can use that machine learning, the trained machine learning model, to either give fast approximations, for example, in real-time ride sharing, where we want to optimize the allocation of rides, or we can use it to tackle very large-scale problems that would take too much time to solve with purely an optimization model. So then, going a bit further onto those interaction effects. So two promising areas that we see occurring. There's of course a lot more, but one of them where we see a strong fusion of optimization and machine learning is AI-assisted X, where the X can pretty much stand for anything. If we take the example of planning and scheduling, for example, we could imagine a situation where we have a hospital. Our machine learning model is then predicting the inflow and outflow of patients. And we have our optimization model that's going to optimize the planning and scheduling. And then thirdly, we have a human planner that is overseeing the big picture. And through this sort of trinity relationship, we can actually see that there's a very powerful system as a whole, and that is powered by this this combination of machine learning, optimization, and the human, where the human can, for example, make the last-minute judgment calls. Then secondly, digital twins. So those are digital replicas of physical systems. And this market is expected to grow from like 35 billion this year to 380 billion in 2034, according to Gartner. So they're expecting a massive, massive growth over here. And how we can use digital twins is we can, for example, do almost instantaneous simulation or scenario analysis of our physical system. And this is, of course, something that can be very advantageous when you have very large complex systems. For example, in the case of Heineken, we could, for example, use this to basically model our whole supply chain and our warehousing, to model that in a digital twin, and then we can make sure that we build a very robust supply chain and get the beer to our customers in the at the most efficient cost. And that's something that's currently not possible without a digital twin, I would say. Then, let's now imagine that we're building a tool and we want to optimize our prices, for example, at Heineken. We collect some raw data, we store that raw data, and we feed it into frameworks such as Polars, where we do some feature engineering. Then, those features we then feed to our machine learning model. So, for example, maybe we're training a neural network, and we follow all the best practices, everything is going well. We then have our machine learning model that, for example, outputs some probabilities of what the different sales volumes are going to be at different price points. But of course, those are only probabilities, and the business is looking at us on what the best way to act. So what would the optimal prices be? So we need some operations research or optimization algorithm to basically give us those optimal price points to set. We deploy this into production, and then
and this is when the problems start to happen. Okay. First of all, is it so simple to just combine this machine learning-based model and use it as input to the optimizer? The way I ask this question suggests that it is not, so let's break it down. Basically, if we treat this machine learning training problem, I mean, if we use the same principles as it was a Kaggle competition, just using some global performance metrics to assess its quality, it is a recipe for a disaster. And I have nothing against Kaggle competitions, it is a great platform. But let's take a look at this example, okay? A very simple one. We have a supervised learning problem. For example, a random forest or the another trees ensemble. And just for the illustration, let's assume that it is underfitted a bit. Okay, so it failed to capture some important relationships between the predicted variable and the predictors because of lack of complexity. But it works also. It will be just better visible for this case. Now we checked some global performance metric like R², for example, and it looked fine. Just to make sure that the model performs equally well for the entire domain of predictions, we take a look at this calibration plot. This is something that you may have seen in the other talk today. So basically here on the x-axis, we see the bins of prediction ranges, and on the y-axis, we have box plots illustrating the distributions of the actual values. So for the model that is performing equally well for any range of predictions, those box plots should follow perfectly the green line on the plot. Okay? So in our case, it doesn't look bad. There are some deviations on the left and right-hand side, but Overall, it is not alarming. However, now if we overlap the histogram of the predictions with the corresponding actual values, we see it is not the case here, right? It is even more extreme on the tails of this distribution. And if it was just a ranking problem, if the model was unable to order the observations in the correct way, it would be fine, right? But in our case, if we use it as the input to the optimizer, it is not fine, because we implicitly assume that the quality of each prediction is the same for any observation, for any data we put into the optimizer, because optimizer doesn't care about how reliable is the given scalar value it gets. And imagine we can have, for example, thousands of such decision variables. So the errors are stacking. And in this case, how to fix it? I am in a fortunate position that I generated this data myself, so I knew how to fix it. It was a linear relationship, so I replaced it with ordinary least squares regression. And you see on the right side, it looks much better. Overall, the systematic approaches to this, mostly referring to classifiers, but similar approaches we can do for regression, involve transformation of the predictions. So we apply some nonlinear transformation, often monotonic, so we get more calibrated outputs from the model, often for the cost of getting a lower original goodness of fit metric or some validation metric we use for training the model, because it is another objective. Obviously, we can also just tune the model against some calibration metric directly, so if it's our goal, we can do this, or just simply use the model that fits the problem better, just like in the aforementioned example. The another one is even simpler. We have now one single regression tree, and it has a very simple task. There is one feature bimodally distributed, okay? You can possibly recognize it is a mixture of two normal distributions, and the relationship between the response and the predictor is very simple. It is linear, with some random noise added here. Oh. Okay? It turns out that for such a model, it is not easy, actually, as we can anticipate. For a regression tree, it is lacking continuity in its outputs, especially for this part of the domain. We do not have a lot of observations there, so this is some source of additional uncertainty for us. And now if we take a look at the marginal effect curve of this feature, it is just one-dimensional, so the partial dependence plot is just showing, basically it shows us the predictions against the values of this feature in its entire domain. We see here this big leap that illustrates the unstable behavior of the model. And again, in the ranking problem, it would not be any problem, right? Any issue, because if the ordering is preserved, it is fine. But here, if we put the observation from this part of the domain to the optimizer, we will get prediction that is either 2.5 or something, or 7.5, which is completely different. And again, we can easily accumulate, we can easily stack errors just because we have different levels of uncertainty for different part of the features domain. And overall, what we can do is, it is just one type of uncertainty, but we should be aware that typically if we put some values, some scalar values into the optimizer, it doesn't care about its uncertainty, right? It assumes that all the points are equally reliable, and sometimes it is not the case. Now, something that happens also in machine learning projects alone. Again, we have a nice linear relationship. We modeled it with a linear regression. It fits the historical data pretty perfect. But this very well-known idea of concept drift may happen in practical use cases and may be particularly harmful when combined with optimization. Okay, so what happened in the future is that relationship between the values of y have changed conditionally on the feature. The practical example, if we are, for example, modeling the effectiveness of our historical promotional campaigns to find this sweet spot, which of the campaigns are more effective, let's assume that we have done this, but there may be some factors that are not under our control, such as changes in the policy of the competitors' pricing strategy. Okay, if they change their price, the sensitivity of our customers to our promotions may change, and this will make our model inaccurate. The another example, in marketing mix models, this is what we typically do at Heineken. The typical product of it is we estimate so-called response curves, which measure the incremental change in sales of our products, depending on how much money we will invest in some marketing channels on our advertisements. So if we model it, it is fine. We know how this response looks like, but the effectiveness of different channels may change in time. For example, they can become better personalized, they can be better designed or reaching the target audience in a better way. So this also can cause this shift to happen. And similarly, the features themselves can also shift. Okay? So the distribution in time may change. If we have some promotions that we collected historically, it may happen that in the future, the company will decide to start running bigger promotions because the market became more competitive. And this will be just basically this will generate new data points that our model will not be aware of in its original training set. Similarly, something similar can happen in our other example for marketing, but overall, those shifts may happen because we made some intervention or for some factors that are not under our control. And in the former case, the feedback loop looks like the following. We trained the model, and based on this model, we produced some recommendations based on its predictions. Then we use those predictions to apply those recommendations in the real world. And we change the world, we intervene. And in the end, we also change the data generating process. And now our future models will have to deal with this change. So, for example, if we optimized our promotional strategies, so we know what is the sweet spot, what is the optimal size of the promotion, we can possibly discontinue the future campaigns that are bigger or smaller than this sweet spot, and our future models may be not aware of its efficiency, maybe not be able to model it. And what we can do is just keeping the best practices. So we should refresh our models, monitor the data, the key performance metrics, just as it is an ordinary machine learning model, and sometimes even perform some manual adjustments if we know that some shifts may happen in the future. Like, for example, if we know that the inflation rate is growing or is going to stay at some level during pandemic or such situations. The last one, to avoid maybe running out of time, it is related to something that maybe not an issue if we only care about the predictive performance of the model. Okay, so if we want only to have the predictions to be accurate, if our predictors are not independent with each other, it is not an issue. I mean, as long as it is not causing any instability problems in the model training phase, it is fine. But in the decision making, based on the optimizer, we often want to know the marginal effect, for example, of what is the change if we increase, let's say, the spends, the investments on our digital advertisements by the given number. And the problem is, like, for example, if we are selling ice cream and we are running our campaigns only in summer without some randomized design, it will be hard to tell if what is the actual effect of increase in sales. Was it the temperature that was greater than for the rest of the year? Or was it the effect of our increased media investments? And in such a case, because we cannot control the weather, I mean, as a human species, we do this unwillingly a bit, unfortunately, but the other factor we put into making smarter decisions is the only one that we can actually control. So in such a case, we cannot tell those effects from each other, and this is a problem because it will also bias the values that we will use for the optimization. So how to deal with this? The ordinary ways of dealing with this, like reducing the dimensionality of the model or regularizing it, of course, can help, at least to make the impact of those correlations less severe. For some of the models, we can try to induce human knowledge, like in the Bayesian regression models. Sometimes we know what direction of the effect to expect. Like in the aforementioned example, we know that typically people consume more ice creams if it is hot, so if we have such a variable in this model, we can assume that this effect will be positive. So eventually we limitate the size of the solution space. And for the tree-based models, we have monotonic constraints, which is also pretty useful because those models are widely used. So we can locally assume the direction in which we want the trees to make the split for the given variable. Okay? So it also introduces some bias into the model, but on the other hand, it reduces its variance, so the model should be a bit more stable. So finally, we can answer this question. Now we know that combining the machine learning algorithm and by using its outputs as the input to the optimizer is maybe not that simple, but now at least we recognize some of the issues. Not the comprehensive, very comprehensive, not the complete list of it, but hopefully the next time we'll have to deal with this, we'll be better prepared. And from our side, that's it. We hope that you like the talk, and thanks for coming there. Thank you.
Thank you guys for an interesting talk. So we have some time for any questions.
Yeah, thank you for the talk. A very, very interesting subject, I think. A question that I was having was, so it's very difficult then, of course, to match, say, the machine learning model with the optimization problem. So when you pick some kind of machine learning model or some kind of auto model to make the predictions, and then you run your MIP, do you guys do some kind of testing on okay, how robust is our MIP right now to say wrong calibration or any of the other problems that you mentioned?
Okay, this is a very valid question. So in one of the applications we use, it is for allocating the optimal budget based on the marketing mix models. We have two approaches. One, it is at the moment when we validate the models before we put them into optimizer, we have interactive dash application for diagnosing the Bayesian models we put inside. So we diagnose its convergence, its credible intervals, and so some key metrics for assessing this. However, in this application, it is hard to design a randomized experiment. So it's also, because we have quite limited data, the marketing mix models often work on the weekly data, so the number of data points is limited. It's just hard to measure it sometimes. And we have to deal with those correlations, just assuming that it is still better than doing nothing. We have to, let's say, agree with this that those measurements will not be perfect. But overall, it would be best, I think, to, if it is applicable, to run the randomized experiment to measure the causal effect of applying this optimization in real life.
Thank you.
I think we have time for one more question.
We have the
I don't want to walk.
So if you mitigate all these issues and then you get, let's say, an optimal solution to make a decision, what if that optimal or mathematically optimal solution is not really applicable in business terms? Let's say they tell you bump up the budget from, let's say, Google advertisement to 0, or slim down the budget to 0, and bump up some other channel really, really high. And that's something, let's say, a business stakeholder would not follow because they still want to engage with Google. And it's maybe mathematically optimal, but it's not something which like a business person would consider. It's like, how do you mitigate that issue? Or do you find other, maybe less optimal solutions, but are still good? Mm-hmm. Like, how do you handle this?
Okay, another very good question. So I will partially answer this and let Stanley answer the rest of it. So when we are still at the phase of training the model, we are not only using, again, such a global metric like R², for example, to assess it. We often also do, but in the end, there are other metrics, like, for example, in the context of MMMs, they are based on measuring the deviation of the effect estimated by the model compared to the, for example, historical spends for the given marketing channel, which is the different target, but we can, for example, before we apply such a model to the optimizer, we can identify those ones that produce completely unreliable ROIs, for example, that do not make any sense because of some correlations or some misspecification of the model produce something that is unlikely to be true. About the part of the optimization.
Yeah, so it's currently, as far as I'm concerned, not possible to feed like probabilities, let's say, or probability distribution to an MILP model. So what you can typically do is you take samples from your probability distribution from your machine learning model, and you can basically, in a sort of simulation manner, feed those, sampled numbers. You can feed those to the optimization model, and then you, of course, get a slightly different output the whole time. But then you can at least protect against the worst case scenarios, let's say.
All right, thank you.
All right, thank you, guys. So we'll be please clap. You clap for that. Thank you, guys. So we'll be starting with a keynote in the Rembrandt. If you can approach Rembrandt, please.